Okay, today we're going to be looking at force momentum problems. We're going to be utilizing the Newton's second law equation, F equals m times a. And we're also going to be looking at momentum problems using P equals m times v. Now, we've also learned a couple of other equations, such as the acceleration equation, Vf minus Vi divided by t. And we've also learned the equation for speed, which is V equals d divided by t. So we are going to have to start by listing variables, okay, in the problems. And so here we have Newton's second law problems. And here, again, we can go number hunting. We have a 40 kilogram mass. Now, kilograms is the unit of mass, so I'm going to assign this to m. Remember, the first step in showing your work is to list variables given in the problem. Then it also gives me 60 newtons, okay, which is our unit of force. And it says, what's the acceleration? Okay, and so we're looking for A. Now, in our equation, F equals m times A, we could use the triangle to rearrange where m times A is on the bottom and F is on top. So if I wanted to solve for A, I'd cover up A with my thumb and it would leave me A equals F divided by M, or F over M. So A equals F over M, where a force is divided by a mass. And then at this point, we are ready to plug in. So we're going to plug in 60 newtons and divide it by our mass, 40.0 kilograms. And it's important to remember that 1 newton is equal to 1 kilogram times a meter per second squared. So in taking a newton and dividing it by kilograms, we're actually canceling the kilogram portion, and we're going to end up with meters per second squared. So here, 60 divided by 40 gives me 1.5 meters per second squared. Now, question 2. Here, we're given 1,200 kilograms. So 1,200 kilograms, that's a mass, because kilograms is a unit of mass. And then it says it accelerates with a rate of 30 meters per second squared. Or sorry, 3 meters per second squared. So our acceleration, 3.0 meters per second squared. And we are looking for the net force. So we know F equals m times A. And here we're going to plug in 1,200 kilograms times our acceleration, which is 3.0 meters per second squared. And 1,200 times 3 gets me 3,600. And a kilogram times a meter per second squared is the unit, which is equivalent to 3,600 newtons. Another example problem here. Again, remember, number hunting is a pretty good strategy where we have 825 newtons. So newtons is the unit of force, 825 newtons. And we have this acceleration unit, 11 meters per second squared. Meters per second squared being the unit of acceleration. It says, what's the mass of the crash test dummy if an airbag exerts 825 newtons of force to decelerate? So we're looking for the mass here. Now, taking that equation from the equation list where F is m times a, here we're solving for mass, so imagine covering up mass. We would then have mass equal to a force divided by an acceleration. And here we would then have 825 newtons divided by 11 meters per second squared. Again, remember a newton is a kilogram times a meters per second squared. So with our standard units here, we're actually canceling meters per second squared. I'm going to write that out so you guys can clearly see. So here, with it written out, you clearly see the equivalent unit of a newton, kilogram meters per second squared, cancels the unit meters per second squared, leaving us with just the unit kilograms, which is our unit of mass. So 825 divided by 11 gives me 75 kilograms for the mass. So those were all, the first three example problems were all examples just using F equals m times a. But here, the second section, or this last problem on force equals mass times acceleration, we have a bicyclist that takes 8 seconds. So here, number hunting, 8 seconds is a time. To accelerate from rest. So rest means 0. So that means our initial speed, the from, is 0 meters per second to a speed of 4 meters per second. So that's our final speed. And says if the mass of the bicycle and rider together is 85 kilograms, what's the net force? And so we're looking for a force. Now, if I'm looking at all of my problems, I know that, or all the equations, I know F equals m times a, and I'm trying to solve for a force, but I don't have a force, or I don't have everything I need for force because I don't have an A. Okay, but however, I do have A equals VF minus VI divided by T. So I can solve for an acceleration because I do have two speeds, the from rest and 4 meters per second in an amount of time. And so here we're going to take 4.0 meters per second, subtracting 0 meters per second, and divide it by the 8 seconds, which gives us an acceleration of 0.5 meters per second squared. So now after I've solved for my acceleration, I can then use Newton's second law equation, that F equals m times a. And I can plug in the 85 kilograms times the 0.5 meters per second squared. And so 85 times 0.5 gives me 42.5 newtons of force. So that last example problem is one where as we get further into physics, we know how to solve for more and more variables, and so this is why you need to list out your variables from the problem to see which equations we can use. So here we have, what is the momentum of a 30 kilogram ball moving at 10 meters per second? So we have 30 kilograms, that's a mass. And I have 10 meters per second, so that's a speed. Remember, that's not an acceleration because acceleration is meters per second squared. And it wants to know what the momentum is. So this is just P equals M times V, where we're going to plug in 30 kilograms times 10 meters per second, which our momentum then comes out to be 300. And the units, nothing cancels, it's just kilograms times meters per second. And so we have solved for the momentum. My second example problem here, we said if a bicyclist has a momentum of 4,800 kilogram meters per second, so we have a P, the momentum variable, 4,800 kilogram meters per second, and a mass of 160 kilograms. So again, we're just kind of number hunting. What's the speed? And so here we're looking for a V. So if we take our base equation for momentum, M and V are on the same level, so they'd be on the bottom of my triangle to help rearrange. And I'm trying to solve for the speed, and so that shows that I would have speed is equal to a momentum divided by a mass. And so we're going to plug in 4,800 kilograms times meters per second, all being divided by 160 kilograms. And that gives me a speed of 30. And here, kilograms will cancel with kilograms, and you're left with just the speed unit in meters per second. And that's our answer. If I look at the example problem number 3, here it says, what's the mass? So I know I'm looking for M. I see 5,500 kilogram meters per second. And so I know that's a P because that's the units, kilograms meters per second. And I see 15 meters per second. Excuse me. So I know that's a speed because the unit's meters per second. So here, again, we're going to have to rearrange that momentum equation. And so if I'm solving for M, cover M up, that gives me P over V. And so I'll plug into my equation 5,500 kilogram meters per second divided by 15 meters per second. And we see the unit, meters per second, cancels with the meters per second. So 5,500 divided by 15 gives me a mass of 366.7 kilograms. And one last equation here, a question, it reads, what is the momentum, right? So we're looking for P of a 50 kilograms, so that's a mass. That travels 16 meters. Now, meters is a distance, so I have to assign that to D. In 5 seconds. So we have time of 5 seconds. So here, I don't have a speed, but I do have V equals D divided by T. And so I can first solve for the speed, 16 meters divided by 5 seconds, which is 3.2 meters per second. And then now that I have a speed and a mass, I can plug in 50 kilograms times 3.2 meters per second. And I get the answer of 160 kilogram meters per second. So these are your example problems for Newton's second law, solving for force, mass, and accelerations, and for momentum problems. Remember, on your work, list out your variables, state the equations, substitute in, and give me answers with units in order to receive credit.